As yet, nobody's built a better mousetrap, at least not in my experience, and I have lots of recent experience, unfortunately. However, I'm very excited with our next presentation because David Mitlyng of Xairos is in the process of building a better GPS, and it sounds very exciting. David, please.
Yes, no, I appreciate the opportunity to come here, especially with the theme of this conference. I want to talk not just about the kind of the application and the problem we're solving, which is GPS and it's a problem, but just a little bit of background on on quantum. There's a lot of hype out there about quantum, so. I actually put together, upon the organizer's request, I actually put together a bit of a white paper that gives our perspective on where quantum technologies are today, talks a little bit about that. But I'm going to highlight that in the presentation today. And based off of what I'm kind of hearing with some of the other presentations, I'm going to talk about the technology, but also talk about the applications. And this specific application is time transfer, and the specific problem it's solving is the limitations of GPS. So you may not know it, but we're in 2025. We're now in what the UN has designated the International Year of Quantum. And that's because in 1925, 100 years ago, there was a series of papers, kicked off by Heisenberg, that really started laying the foundations for this brand new field known as quantum mechanics. I think about just how everybody is blown away by where it was only 60 years from the Wright brothers flying a Kitty Hawk to putting a person on the moon, but going from 100 years to that original foundation to where we are today, manipulating and using quantum technologies for very major applications and advancements in our lives is really, I think, a lot more mind-blowing even than that. So when Heisenberg originally came out with some of the papers, it was based around this idea that, when we think of quantum, we all know it's hard, right? It's the concept we struggle with, and part of the reason we struggle with it is because quantum effects are weird compared to our understanding of the classical world, the universe we live in. Heisenberg's paper said, we're all used to kind of classic Keplerian orbital mechanics. The Earth goes around the sun, the moon goes around the Earth, satellites go around the Earth, and if we know the position and velocity of a satellite at one moment, where it's going to be an hour from now, it's going to be 24 hours from now. That's classical physics. But they had a problem with looking at an atom. Like the atom was a relatively kind of new discovery, so to speak. And if you had an electron going around a proton, the math didn't work out. The electron should spiral into the proton, and atoms should not exist. So they knew something strange was going on there. And so with some papers, they realized that the electron's not going around the atom, it's around the atom. It's not in a position, it's in a superposition. It's smeared over that orbit all at once, all at one time, until you observe it, then it collapses into one position. So that started off a whole slew of other papers, and then you got the uncertainty principle, you got Schrodinger's the Schrodinger function and the wave function equations. You got entanglement. Entanglement actually came out of a thought experiment by Einstein, 5 years later, because he was unhappy with some aspects of quantum mechanics. And so he wrote a thought paper that kind of invented entanglement. But in my mind, I think we're not 100 years from where quantum mechanics was discovered. Really, quantum mechanics was discovered in 1905 with a paper by, again, Albert Einstein, where he realized that light isn't a wave like people thought at the time. You had the double slit experiment, and light interfered on itself to create diffraction patterns. Light has a discrete particle called a photon, what he called the Lie quanta. And that quanta became quantum mechanics. So all these guys, they were all kind of out of Copenhagen and Vienna and everything. They all collaborated. They created the framework for it. Again, part of the reason we all hate quantum mechanics is the language they used to describe it was very complicated math instead of trying to understand what the heck was going on there. But the hard math and the fact that you can't really observe what's going on because the wave function collapsed, and because it happens at something very small, you didn't have the instrumentation at the time to really see what's going on. And there's some people that think you will never, ever be able to tell what's going on. It's a quantum weirdness that you will never be able to detect. Really is what created the mystique around it today. And all of that was kind of that first tranche of development. And that, I put 1950 on there, but really, that all kind of ended in 1939. Oh, there we go. And that's because of the advent of World War II. All these scientists that were working and collaborating together and just making rapid discoveries, Europe collapsed, they all fled to their different corners. And in Europe and in the US, they started the Manhattan Project, the development of the atomic bomb. Now you had quantum mechanics, and it was all in this theoretical world, and they said, we need to understand, we need to put a lot of money into this because splitting an atom, that quantum effects, is something we need to put a lot of research into. And that changed the whole dynamic of the quantum trajectory. Now scientists weren't trying to try to figure out what's going on in the world of quantum, what's really going on behind the scenes. They're just trying to use it. You know, it went from theorists to experimentalists. And the side effect of that, the positive side effect is that we're all benefiting from that today. You know, that research that went into the Manhattan Project, you know, funded a lot of research labs around the world. And that led to kind of that, what they call the first quantum revolution. The revolution that led to semiconductors, it led to atomic clocks, it led to MRIs and lasers. I'll talk a lot about lasers, but you know, going back to photons and the importance of photons, this idea that you can, you know, it's easy to create a photon. You know, cavemen have been doing it since the beginning of time. You start a fire, you're releasing photons, billions of them flying off in all directions, all different colors going off in all directions. The laser was really the first time where we actually harnessed the individual photon, got them moving along in an orderly fashion, and all of the same color. A red laser is fundamentally, 800 nanometer wavelength, you know, bunch of photons, all marching in orderly fashion. So you can imagine kind of like what our world would be like without some of that work and experimentation that's led to the laser, semiconductor, and things like that. Now today we're in a whole different paradigm. When we talk about the second quantum revolution, it's not just, you know, taking and understanding how quantum works, but we're at a stage now where we're actually controlling the quantum properties of particles. And that's why there's a lot of excitement going around with quantum and quantum technologies. We all just had lunch, so maybe I'll do a quick survey here. But you know, I have a colleague that claims that quantum technologies will be to the 21st century what the semiconductor was to the 20th century. Now, I just kind of survey, just raise of hands. Do you agree? Do people agree with that statement? A couple people do. I think most people aren't raising their hands because there is a lot of hype around quantum technologies. And besides, FYI, depending on how you responded, I could argue both sides of it, right? There is a lot of hype around quantum technologies, but I'm definitely one of those people that believe that for all the press we put into AI and this and this and this, quantum technologies is fundamentally going to transform our life in a much more material way than anything else we're all kind of considering. Now, I think a lot of the reason that people believe that quantum is in a bit of a hype bubble is because of quantum computing. So I just want to be very clear, what we're doing at Xairos, we're not quantum computing. I always get that confusion with people. There's really kind of three main branches of quantum, and quantum computing gets all the investment, they get all the press, they get all the interest from everybody. And of the kind of three different quantum technologies out there, quantum computing is the least mature, by far. Again, I don't want to talk a lot more about this because I'm not a quantum computing expert, and also there's a lot of press out there, and you guys are all looking at that anyway. The one thing I like to highlight with quantum computing is the biggest misperception about it is just it's a better computer. It's not a PC. It's not going to do what a PC or supercomputers or data centers do. Quantum computers are fundamentally kind of using entanglement or kind of the quantum properties of particles for kind of optimization type algorithms. And that's part of the reason that people believe there's a lot of hype around it. Number one, it's fairly immature. It's going to be a long ways away before it really scales to do anything meaningful. But even within the quantum computing companies, they'll struggle to tell you what the application is going to be for quantum computers. One of the most well-known applications actually is an ability to factor prime numbers. That's interesting because this is something that was realized a decade or two ago. 1994. Yep, 1994. Yep, Shor's algorithm. Yeah. It's this idea that if I have a prime number, let's say, or let me rephrase that. Let's start with an application. If I want to send a message, a secure encrypted message to Nancy. Nancy's in the back of the room. We both have a prime number. Only the two of us know this large prime number. And I want to encrypt that message. So I create a new prime number. That's the prime number that is going to use to encrypt the message. And I have to send it to Nancy. Nancy's a long ways away. She's over in the East Coast. I'm in Colorado. So I multiply our known prime number with that prime with a new prime number. It creates a new, very large prime number. I send that to her. You guys intercept it, but you can't factor it. Trying to factor two large prime numbers from one large prime number is nigh impossible with today's computers. A quantum computer could do it in seconds. So, and the factorization of prime numbers is the basis of our all encryption today. So people are understandably nervous about the capabilities of quantum computers because all of our public key infrastructure is going to, they call it Q-Day. It'll collapse once quantum computers get to that point. Articles have said, quantum computers need to get about 4,000 qubits before they can do it, maybe crack a 128-bit key, public key. And quantum computers, you guys know, is probably like, they're what, 100, 150 qubits today. So either be stressed out or not, whatever. But there is a sense that that day is going to come, and when it comes, we'll panic then. And there are other applications they're looking at with quantum computers, but most of the articles I've seen said you need to be about roughly 1 million qubits before you can really do some of these very impressive kind of life-changing optimization algorithms. So that's my quick talk about quantum computing. I think what's more interesting and kind of slept on is both quantum sensing and quantum communications, the area I'm in. So quantum sensing is kind of a similar, kind of using kind of similar kind of hardware, typically cold atoms, the quantum properties of ions or trapped ions or atoms for very, very sensitive sensing applications. They're also that's also lumped in too with very accurate clocks, CSACs, optical lattice clocks, things like that. By using the quantum properties of these particles, now you get super stable, accurate clocks. If you go to NIST out in Boulder, Colorado, you can see their F2 fountain clock. I think it's accurate. It keeps time within, a second within, the lifespan of the universe, something crazy like that. But the other ones that are being developed that are very, very interesting, and these are being developed by partner companies of ours, so I know a little bit more about them. There's quantum RF sensors that are out there. These are very sensitive wideband sensors, RF sensors that, much more sensitive than the antenna you have in your cell phone. You can imagine, you're out in the middle of the mountains and you could pick up a signal coming from anywhere with just very good signal to noise ratio, but also very wideband. There's also a lot of work being done with gravity gradient and magnetic field sensors. I was talking to a colleague the other day that they're working on these, that they're getting sensitive enough now that you could use them, again, going to the application side of things, you could use them, kind of take them over the ground and measure the fine gradient in the gravity or magnetic field to detect, say, tunnels, subterranean structures. But what's more valuable is mineral and oil exploration. They're that sensitive. Now, a lot of good quality companies working on this. They're getting very good government funding. I think the venture and private community are kind of catching up to them. But the fundamental problem with these is that they're a bit too large, right? They're not compact enough that you can put them in your something transportable. They still got to be a little bit. They're definitely not small enough that you can put that quantum RF sensor in your phone yet. But once you get there, then of course you imagine what a game changer that's going to be. Just even for using it for applications that we use every day. Now I'm in the realm of quantum communications, which is photons, the quantum properties of photons, primarily for security applications, but also for creating really more around security. The value of dealing with the quantum properties of photons is that, okay, even if they're kind of fundamentally random, there's a security inherent with having having encoding in the quantum properties of the photon, because you can only measure it once. That's like a foundational property of all quantum mechanics. It's called the no cloning theorem. So, going back to kind of one application, you can use it to create truly fundamentally random numbers. You can use it to distribute encryption keys. You could use it for quantum radar, quantum LiDAR. Our application that we focused on is time, but there's also some very interesting future applications that go above and beyond that. And now this is absolutely the most mature of the quantum technologies, because you're leveraging laser and optical systems that have been now around since the 50s and 60s, and piggybacking off that capability. The breakthrough really with all quantum, or the majority of the quantum communication systems, is this thing right here. This is a source of entangled photons. Now, again, you guys probably watch all the YouTube pop sci things on entanglement. There's all kinds of crazy stories about the magic of entanglement. Fundamentally, if two particles are entangled, maximally entangled, number one, to be clear, to be entangled means you have to be entangled in certain quantum states. Entangled in polarization, entangled in time energy. So when somebody says they're entangled, impress them by saying, entangled in what quantum state? So that way they'll be very impressed. But we have the ability now to create entangled photons, and fundamentally the way it works, this is a source of entangled photons that's created with a process called spontaneous parametric downconversion. Entanglement happens in our lives all around us every day. Anytime you get two particles kind of close to each other, they get some form of entanglement just naturally. With photons, we start with a blue laser spitting out blue photons of roughly 400 nanometer wavelengths. We have a design that uses nonlinear crystals, very carefully designed and cut, basically pieces of fuzzy glass. And those nonlinear crystals converts individual blue photons into pairs of red photons that share the same time and energy. And then by kind of designing some more nonlinear crystals, you put them in that proximity to each other, and then they're entangled. And we deal with, like I said, polarization, entanglement and polarization is just very, very easy to manipulate. It's just super cheap, simple hardware. The other kind of major breakthrough that we're dealing with is the detectors. So when you use laser communications, you're taking a laser, standard laser pointer. You could start with that. And you pulse it on and off to send across zeros and ones. So the zeros are off, ones are on. And the detector you use is, for all intents and purposes, basically a piece of, it's like a solar panel, right? It converts, the photon hits it, outputs a little energy blip. The more photons that hit it, the more electrical signal comes out, and that way, when you're sending those zeros and ones, you're trying to get enough photons to that detector so that you get enough, you can read the signal above the noise floor. The way single photon detectors work, it's just basically kind of a fairly advanced version of that avalanche photodiode, which means every photon that hits it is a click. You get a little pulse of a signal that comes off, and that tells you a photon is coming. And these systems, these technologies have, hardware has been around for a while, primarily spurred for the delivery of encryption keys. So the way the thought process is, you, go to the next one. So the thought process is, I have a source of entangled photons. I'll have a single photon detector where I'm at. Nancy's on the other side of the country. I can send the other pair to her. Maybe I send it via satellite. Maybe I send it via fiber. These are optical, so it's however you want to transport those photons over a laser source. And the value of it is, if I measure the polarization, it's horizontal or vertical, diagonal, anti-diagonal, I know what Nancy has. They're entangled. That's the magic of entanglement. And the majority of those photons will get lost between me and Nancy, but that does make a difference because every photon is a bit. So if I detect 1 billion photons a second and she gets 1,000, hey, we got 1,000 common bits that we share, and we will use that to create a random string of bits. And that random string of bits will create an encryption key. And then Eve, the eavesdropper, that's in between us, will try to intercept those photons meant for Nancy, the way Eve has been used to intercepting those public keys that we're sending back and forth now. But Eve was thwarted because you can only measure that quantum property once. Entanglement's broken. Eve can't measure it and retransmit it. We would do a quick check between us, and we would know that there is an eavesdropper in between there trying to muck with that. So this is, and I use Alice and Bob. That's not our names, but Alice and Bob is kind of the classical terminology in cryptography. So we always use Alice, Bob, and Eve. So there you go. Now what we're doing at Xairos is a little bit different than that. So QKD has been around forever. QKD was quote unquote invented in a paper in 1984. The entanglement type QKD was a paper that came out in 1991. The hardware caught up to it in the last couple decades. I had a conversation with somebody a little bit ago about, well, okay, well, what's the maturity of it? Well, you can go buy it today. These are off-the-shelf components you can buy, install in your networks. You can start moving around encryption keys today. Definitely when quantum computers start getting to the point of being able to crack public key encryption, then people are going to have a big rush, big rush to buy those equipment. Unlike public key encryption or other types of software-based, encryption delivery schemes, QKD just fundamentally can't be cracked. If you could crack it, you're going to win a Nobel Prize because you've figured out something that Einstein and Born and Schrodinger couldn't figure out. So you got that, looking forward to it. But I'm not looking at doing that. I'm looking at using it not to distribute keys or distribute randomness. I'm using it to distribute time. So this is where I kind of want to shift gears a little bit and talk about time. Talk about quantum, talk about time, and the importance of time for our modern world. Now, the fundamental, use case for transferring time, if I'm going to transfer time to you, we're all in the same room. I'd say, it's 12:48 p.m. at this mark, bap. And you'd all your clocks are all wrong. You all synchronize your clocks. Great, your clocks are all synchronized. Time transfer is trivially easy when the clocks are close to each other. It's incredibly hard, especially at a very good quality of accuracy and precision over long distances. So we are fortunate that we live in a world where just about the time we all realized we needed to synchronize our clocks, along came a brand new satellite constellation sponsored by the US military, specifically to drop 2 bombs through 1 door after the Vietnam War, called GPS. So it was just serendipitous that at an era where we're going from analog to digital networks, and we started to really need accurate synchronization, was about the time that we had this clock in the sky available to us, and a time transfer method developed for what they call position navigation and timing with the GPS constellation. Now, time transfer, like I said, kind of all works the same way. There's a few different ways to do it. You can do it with RF signals, you can do it with optical signals, you can do it whatever, but usually you basically, a change of phase or a change of pulse allows you to mark what the time is. You send it, over long distances, the person receives it, and if you know the distance between you and them, the latency, so to speak, that's what you could use to synchronize the clocks. And you have to kind of transfer your time as well as those little marcation points. But again, that's fundamentally how all time transfer works. In 2018, my co-founders, brilliant quantum scientists, they said, well, we got this technology. We can detect individual photons. When they're created at a very tight time correlation. We know that GPS is very susceptible to jamming and spoofing. We know that GPS has a fundamental accuracy limit. And that accuracy limit, I could go into gory detail on that, but it's just fundamentally, the best you could do with an RF time transfer. Those waves, get dispersive over the atmosphere, and your nice crisp, change of phase and pulses get a little bit ratty over longer distances, and you go through atmosphere. You don't have to deal with that when you're dealing with individual photons. Each photon is a click. So we've done papers, we've looked at doing time transfer with entangled photons over deep space missions. We looked at it over like cislunar missions. You don't lose any accuracy even over incredibly long distances. You have to get a minimum number of photons between Alice and Bob, but it doesn't degrade the way you would with RF or optical or all other methods of time transfer that exist today. So they invented that in a paper in 2018. That led to some lab experiments with some QKD labs in Singapore. That led to some more papers. That led to a patent. We formed the company around commercializing this in 2019 with a vision that now we have kind of an enabling technology to disrupt and build a better GPS. Again, we highlight a lot the accuracy, right? So what we've done in the lab with very, very simple quantum hardware is we get down to roughly 10 picosecond level accuracy. That's 10 trillionths of a second. So you sit there and say, well, that's ridiculous. Who needs that? But our networks need that. All modern electronics need better synchronization. The previous presentation, we're talking about, the limitations. Doug was talking about that. What do you call the von Neumann gap or whatever? A big reason these data centers, these distributed databases, consume so much power is because the elements in it aren't well synchronized. And Facebook and Meta and NVIDIA have shown that if you synchronize them better, then the bits will flow more efficiently. And there have been other developments that showed that if you get better synchronization within power grids, within PMUs, then they're more efficient. You're losing less power within the power grids. So But fundamentally, even more importantly, that is the security and resiliency aspect of it. GPS is a weak signal. It's 1,000 times weaker than a cell phone signal when you're down to 1 bar. It's easy to jam. You can go on eBay, you can buy $20 GPS jammer, plug it into your cigarette thing. Truck drivers use it all the time. You're jamming GPS for everybody around you. What's really scary with GPS today is what they call spoofing. It's analogous to like phishing emails that you get with your kind of things, where with the advent of software-defined radios and a little bit of kit, for a few $100, you could build a spoofer that makes you think your position is correct, your time is correct. You'd have no idea. Your position will sit there and say, oh, I'm in Chattanooga. Oh, I'm in New York, right? It's very easy for them to spoof it. And with the conflicts going on in Ukraine, the conflicts going on in the Middle East, spoofing has gotten out of hand. There are now reports that particularly in the Baltic areas and the Nordic countries, there are about 10,000 reported incidents of spoofing a month for flights, commercial flights. There are videos, go on YouTube if you don't want to sleep tonight, of pilots cruising along at 35,000 feet, and they're getting terrain warnings, alarms going off in their cockpits because they're being spoofed. They're being, pull up, train ahead, pull up, train ahead. Like it's a nasty problem. So we're looking at using this technology for kind of creating this at a level of accuracy, at a level of security that just you can't touch with GPS or any other RF-based time transfer system. So the way we're doing this is, I kind of already talked about this. I've already given you the panic speech. There's a couple of, there's other, I could go on all day about other examples of this. January 26, 2016, there was a famous incident that operators on the GPS constellation uploaded, had a little bit of a software error, and it degraded and nearly wiped out networks across the world. It knocked out BBC, it knocked out emergency and radio services in the US and North America. Just fundamentally, if GPS went away, like, everybody thinks like, it's gonna be messy, right? Like I'm not gonna be able to get to my favorite restaurant or whatever, but that's not the problem. The problem is the time, the clock. Instantly, and I mean instantly, all financial transactions would halt. They need that time reference to do their thing. ATMs would halt, credit cards would halt, cash. Your internet and cell would go down probably within a day or two, depending on the quality of the network and the holdover of the quality of the clocks they have in their network. And within a week, power grids will go down and it's Mad Max, right? We're all running around just waiting for the end. So this is a very well-known problem, definitely within the US military. I'm going to these conferences, that's all they talk about. And what makes it even scary is with the global conflicts going on, China in particular, they built their own GPS replacement. It went online a couple years ago. They're giving away receivers to all their allied countries, and they have a date. No joke, I was at a briefing, an on-class briefing, where they have a countdown clock at Space Systems Command in Colorado Springs that's counting down to January 1st, 2027. So enjoy New Year's Eve on 2026, because they have a countdown clock going down to that date, because that's the day when they think GPS will be threatened. So, so we're looking at this not as a technology. It's an interesting technology, no doubt. We could wax on about the craziness of entanglement till we're blue in the face, but as a group, we're focused now on an architecture that makes sense as something that could replace, augment at first, but then replace GPS. And it starts with Alice and Bob as a satellite and ground. So now I got a clock in the sky, or maybe the clock's on the ground, right? It's a UTC reference at NIST and Boulder. It synchronizes the clock we have in the sky. We have that quantum link there. Then from that clock in the sky, also from that reference, we could also synchronize over fiber networks locally. We can then also synchronize within common view of the satellites. So we have the satellite over North America, it synchronizes all the points in the ground, so we get fiber as well as space-based. Satellite would also have like an RF layer on top of that. And then you got, you sit there and say, well, what about my mobile device? Well, Once you synchronize cell towers, base stations, particularly in urban areas, if you can get that accurately synchronized, get it down to picosecond level synchronization, those cell towers can provide that what they call last mile position, navigation, and timing signal. It's already in the chipsets in most of your phones. You have a good quality smartphone, it's already getting its position from local towers around here. But if you get that synchronized to that level of precision, then you're getting your position knowledge to, instead of a few centimeters, you're getting it down to a centimeter. And because the cell signals are strong, especially in urban areas, you can get your position knowledge down within, indoors. You can get it in underground garages. You can then start looking at a world where we can have, self-driving vehicles, and they can park underground. You could have delivery drones. Have a delivery drone deliver you a pizza at your desk in your building. You can have industrial robotics, as well as kind of the synchronization of networks. Yes, Tony.
Maybe I missed something along the way, but are you talking about something that exists today, or this is what you're building, or what's... January 1, 2027 doesn't seem very long. That doesn't seem very far away. So I'm hoping this is...
We're building as quick as we can. So we're, I feel like we've come a long way since 2019, but right now we have some very nice contracts, but they're all kind of government agency contracts, right? Space Force, Air Force, NASA. We got a contract with Space Development Agency, and we have 2 European Space Agency contracts. We have a Netherlands Ministry of Defense contract. So long story short, we're building it, but we're terribly underfunded.
Do you mind if I ask?
Please.
OP, are you interested in this?
We've been interested in this for a while, yes. They've been tracking both this and quantum sensing, I think, are 2 very interesting areas.
Yes.
So just a couple questions about the system. The first is, because you are using laser links, when you talked about base stations, you do require line of sight. Is that correct?
Correct.
And second is, if you're using laser linkages, that means that you're going to need to transmit fire, whatever the verb is there. You're going to need to get a laser from a satellite to each of these optical receivers.
Yes.
So you're going to need satellites with lots and lots of lasers on them.
Yes. Fundamentally, yes. But one of the things we like about this architecture is, this is called a super GPS architecture, by the way, based on a paper out of TU Delft, is you only need about a couple seconds to synchronize the clock. So the thought process is we can put the kit on somebody else's satellite, and you also got the fiber networks too to do the synchronization, and then sync. So we're syncing New York to San Francisco to Buenos Aires, Common View to... So it's a much simpler concept of operations than your typical optical communications or even QKD. There are space-based QKD missions too, by the way, that are being developed. Yes?
What happens when it's cloudy? What happens when it's cloudy?
You can't get a link with clouds. So that's why you kind of have to have a diversity of sites, what we call diversity of sites. So, okay, it's cloudy here in Nashville, then maybe it's clear in Atlanta. We synchronize Atlanta, and then Atlanta synchronizes Nashville, kind of thing. Yeah. And it's nice because you only need to get about 10 seconds of clear sky to synchronize. So, but again, you guys have been, if you live in the Midwest, you probably never get 10 seconds of clear skies, winter time. So it's but there's potentially, we could penetrate thin clouds. So but you're right, clouds is a problem. And I could also talk to, there's also some development going on at entanglement sources at millimeter wavelengths, which tend to go through clouds fairly well. But detectors kind of limit that. So yeah, so the nice thing is about the projects we have funded, they're developing the commercial hardware. We're very, very commercially focused as a company, right? We're not doing things because we care about military thing. The military things funds our commercial vision. And we got a timeline. I think we're close to getting funding to launch our first satellite. And then we can scale pretty rapidly there. First satellite gets it up there, does it over a region. Then we go to global service, and then last mile P&T is kind of the next step after that. I always like to kind of put a note in there too. We were ahead at one point because we invented the technology, but Chinese researchers have replicated our technology. They've now put it on their fiber networks. They're putting it on their satellites. They're going to MEO and geo orbit with this system. So, but that's kind of the nature of the world, right? They recognize it's an important technology to get out there. So, all right, I think I'm at time, but doop. Okay. Yep. So that's it. What's that?
What orbits?
Well, so China announced in October 2023 they're launching this system to both MEO, which is medium Earth orbit, and GEO orbits. So they're and they got 3 low Earth orbit quantum satellites going up this year. And the MEO and GEO satellites are going up next year. So our system we would look to put on a GEO orbit just because you have a persistent view and a fixed point in the sky. So that's kind of what we're looking at. So.
Is there any indication as to whether the Chinese system would be available beyond their allies?
Yeah, but would you buy that? I mean, I'm not trying to be negative, but the sense I get, or at least with the groups we talk to, is so GPS has been a
I guess I'm wondering,
Yeah.
we're going to end up with like 50 different GPS systems now. Is every country going to need its own because it's no longer going to be a shared resource?
Yeah, that's kind of the movement that's going on right now. Every country is trying to get their own independent system because, and then there's another case that really doesn't make the news much, but when May of last year, the US government shut off GPS over the whole Middle East because of missile attacks into Israel. So the US has kind of used GPS as a soft power tool forever. So it's, the commercial community, this is a big problem for them. They can't count on a resource that's owned by the US military. So.
All right.
All right.
David, good luck.
Okay.